Maybe we start with these two questions. For the first question, I think you can take reference to the Maclaurin series, and then you can exchange the variable. For the second question, we need to apply the coefficient for Maclaurin series. If you remember that all the power series will be having the sum of Cn multiplied by x, right? Or x minus a if you remember the general formula. But since in Maclaurin series a is equal to 0, then you just have the Cn and x to the power of n. So first you need to define the functions in terms of the sum. That's the first step, and then the other one, you need to utilize the coefficient formula for the Maclaurin.
Is the answer for the first one
Yes. Okay. So practically, if you look at number 1, okay, let me break down this. So if we look on the questions, if we simplify this sum, we can write this as 3 over 5 to the power of n over n. And simply, if you remember the ln, 1 plus x, this is precisely the same structure. So by doing so, this is actually equal to ln and 1 plus 3 over 5. Okay. And this becomes ln 8 over 5. So this is the answer. Okay. So whenever you have a question that's asking specifically some of the series, and the series seems like it has a definitive numbers, then you need to use some reference and maybe modify if you need to modify to the reference. So I think the essentials for Maclaurin series is the essential functions that we have discussed last time. Like for example, the 1 over 1 minus x, the ln 1 plus x, the sine, cosine, tangent inverse. Okay. So I think an e to the x also essential. So if you familiar with those factors in the functions for each Maclaurin series, I think for most of the subject questions like this, I think it should be not really complicated. The problem is when you maybe not really know how to make the functions, how to make up the functions out of this sum of the series. In doing so, you can try from 1 over 1 minus x, derive by yourself, and then maybe integrate, derive, and finding how we can get this structure. Okay. Now the second question. Okay. If we can define the functions as x and multiply with 1 over 1 minus x squared. We can define these functions as a sum of the series of 1 over 1 minus x, right? And we can write this as sum and then we can further simplify. Now we have this structure. And what we are going to do is we need to find this, the n equal 1 or 1. Right? So, which means if we're looking the structure 2n plus 1, we want to get 101, so we have to deal with the n equal 50, right? Okay. So from this, let me write x equal 101 is x to n plus 1, so n will be 50. So when n 50, we will have negative 1, 50, x to n plus 1. And since it's an even number, so negative 1 is a positive, so we will have, this is just x 101. The coefficient is just 1, right? Because of the positive, negative 1. So let me write the coefficient. So, which means if we remember the coefficient formula, this will be f n 0 and then 1, or maybe let me write n factorial. And at c 101, this is f 101 0, this is 101 factorial. Okay. So then the coefficient is 1. This is what we are looking for, the f, and then the factorial. So we get the results at the end that this is equal 101 factorial. Okay. So this is just another question aside from determine the function, determine the series. We also can determine the coefficients of each from each Maclaurin series. And also find the sum of the series to be a definitive number. That's the first question, finding the sum of the series. The second question is finding the coefficient. So at least finding the functions, finding the sum of the series, finding coefficient, finding the sum of the series directly, definitive numbers. The other questions probably finding the first three first terms, maybe 3 or 4 first terms of some Maclaurin series. Maybe that's also example of the question. And you will learn more on how we can practice this example. Probably Wednesday or Thursday I will give you the link for some testing, so you can work out some practice. And I think I'm considering for either quiz or homework, but of course it will be the percentage is not as much as the original quiz. But I will look the average score first, and each one of these, how you did the test. Maybe around 15 questions, or maybe 20. Okay. Okay, I think we can move to the next sections. Okay. Okay. So 11. Applications of Taylor polynomials. So for the applications, there are several applications, but I think I will just focus on one application. Okay, so for the Taylor, this is to approximating functions. There are other fields that we can also use the Taylor polynomials, like in physics. But I think I will just focus more on approximating, because I think this is very basic for approximations. Most of the subject of study, they will use the approximations. And since we are using the polynomials, and polynomials is one of the simplest functions that easy to apply. So I think most of the time, I think for computer science or computer scientists, they will use this approximation because they can build it into a system easily because of the function itself. Okay, if we look on the functions, we can define this in terms of sum. Okay, generally we can write this approximations. And then we also remember that we can write the partial sum. Let me use another integer I to differentiate between this f and t. And we can expand this partial sum from 0 to some n. I think I will just make plus okay, since the function f is the sum of its Taylor, and the partial sum t and x, this will approach f of x as n getting larger. So by doing so, I hope you get the idea that we can apply the sum to approximate our function. It's similar to what we have in the linear approximation as well. We use the tangent or the linear equations to approach some of the point in the curve. Okay, if we remember what we did in the, let me just make some short review. So if we have this curve and we have some tangent line like this red one here, it means that if we look on the tangent line, the point here that is touching the curve, Let me make more clear. If the points are nearby this tangent point, that's maybe around here, you will not see any really different line. It seems that it's the same line. Okay. But if we are taking the points too far, we are seeing the gap, right? And that is actually similar case with our approximation in Taylor. So we will have some certain restrictions that probably it will restrict our samplings, how to take some points, and the gap will be determining the remainder or the error. Okay. Okay, and then if we are taking out the first degree of the sum, we will have f of a, and then plus f prime a, x minus a. This is precisely the same as our linear approximation. So actually, if you think in general, the Taylor series is much more general. You can use it for more polynomials, for more degree of polynomials. Linearization is just one part of the Taylor series. Okay? If you think clearly. Okay? So it's not just a different subject, different chapter from all calculus subject. The actual series we can study in more general concept. Okay, so this is the partial sum. So this is also we call the linearization. And then of course, if you add more n, like for example t2, we will have f of a plus f of prime a, x minus a plus f double prime a divided by 2. This is x minus a squared. Okay. We will have a quadratic, and if we have 3, we have a cubic, and so on and so forth. And of course, if we are looking at the graph, let me check the graph whether I take the picture or not. Okay. Okay, let me take example. Okay, let's take example on y equal e to the x. Okay, if you look e to the x, okay. If you remember how we can have the e, we can write as 1 plus x squared over 2 plus x cubed over 3 factorial plus x4 4 factorial plus dot dot dot. And if you look on the partial sums, the t1x is 1 plus x, t2x is 1 plus x squared plus x squared over 2, t3x is 1 plus, it should be x, sorry, 1 plus x squared over 2 plus x cubed over 6. Okay. And if we look on the graph, okay, there are certain points, right, that when you look at the T1, T2, and T3, they all have different gap to the e to the x, to the e, right? But when we look on this point here, 0, 1, this particular point, all the points nearby this 0, 1, they are really, it seems that they are aligned together, right? So which means this is the best way to approximate all these points. So when we have points nearby the 0, 1, you see that's our best approximation. If we are too far, we are really having a gap. But then if you look at how T1, T2, and T3, it seems that they are getting closer and closer to the E itself. But probably if we take T99, as I mentioned, it's actually still they are not really getting in line with the E. Of course they will getting closer, but they are not getting or crossing the E.
Okay, so the best way or the best linear approximation or maybe when we write the tangent line T1, let's say T1 is the tangent line to y equal e to the x at 0, 1. And this tangent line is the best linear approximations to e to the x near 0, 1. Okay. Okay, let me give you the other conclusion and example from this one. Okay, so as I mentioned, we will have some slight error, or we call the remainder. So how good the approximation is, and this is probably also how large we take the n to achieve good accuracy or your desired accuracy. Then this will be determined by the remainder, which is the difference between the functions and the partial sum. Okay. Of course, the first possible solution is we take some time to write down the graph into our computer graph or calculator graph, so we can calculate or graphing the curve and estimate error. Second, we can use the alternating series estimation if it is alternating. Or we can use Taylor's inequality. Which stated that if n plus 1 of x is less equal m, then we will have our remainder is less equal m n plus 1 factorial, and then this will be x minus a and n plus 1. This is what we have. I think last time we discussed this remainder. And the m is just a value that should have, it can be any value for m. But for m to be actually true, then we need to design how will be the error, how much n we need to have, okay? And also design that. So some question will be asking the error itself, or maybe some question asking which n that should achieve certain error. Okay. So let me give you several examples how we can use this, at least 2 and 3. So we can use the alternate series estimation or the Taylor's inequality. It depends on the series. Or actually, if your calculator is on the back, I think you can use some functions on your calculator. There is some functions of calculator. They will have some certain. They will understand the Taylor sometimes, but you need to check. Okay, for example, we have the functions a cubic root of x. Okay, so approximate f of x by Taylor polynomial of degree 2, which means that is the quadratic at a equal 8, and then how accurate this approximation when 7 less equal x less equal 9. So we have the interval from 7 to 9. The question is asking what will be the error. Okay, what will be the error? Of course, the first thing that we need to do when we have the Taylor, if they stated some degree of Taylor, then we need to expand the Taylor first. We need to find the coefficient, and then we need to take the a equal 8 inside the equations for the Taylor series. So first, probably we can write the functions as x 1 over 3. So we can derive this 1 over 3 x and then negative 2 over 3. And then the second derivative negative 2 over 9 x negative 5 over 3. Okay, this is the second degree, but let me just take it to the third degree, because we are needing the third degree for the Taylor's inequality later. So we will have 10 over 27. Okay. And then we need to take the 8 inside and compute. So 8 will be 2, 1 over 12. And then the other one, 64, 32, 1 over 44. 1 over 1 for 44. Now the Taylor for the second degree, the partial sum will be f8 plus f prime 8 divide 1 factorial x minus 8 plus f double prime 8 and then we can exchange this into 2 plus 1 over 12 x minus 8, and then the f double prime, this will be minus 1 over 44, but multiplied by 2, this will be 1 over 288 x minus 8 squared. We can say that this is our approximation of our functions. If we look on the x, if we imagine x is less than 8, it will be not alternating, right? It's not alternating if x is less than 8. So I think we can just go to the Taylor's inequality. Okay. So let me write here Taylor series is not alternating when x is less than 8. So we can use the Taylor's inequality. Taylor's inequality. Okay. Taylor's inequality when n is equal to. And then the m, we will going to introduce the m as this inequality. And since we have interval from 7, okay, because the x should be from 7, now we have x 8 over 3 greater than 7 8 over 3. And so our third derivative is 10 over 27, 1 over x 8 over 3. It will be less equal. Okay. So actually
we did here is basically we need to make some assumptions, right? We need to make some assumptions. What m should we have? So the best way we take this m is by looking at the third degree of the function. Okay? And probably it should be so this f third derivative, they should not be greater than the number of the number of m here. Okay? And then since we have the 7 as our basic interval from 7 to 9, so we take the minimum of x. Okay? So probably if we have the x 8 over 3 greater or equal 7 8 over 3, this is 8 over 3 from this form from the third derivative. So when we have this x 8 over 3, this should be less equal than the number we have applying the interval of x. Okay. So then from here we can estimate, if we can estimate using calculators, that this should be going to have around this number. Okay. So what's this number? What's this number? This number is, we consider this number as our assumption for our m. Okay. So our m is actually our assumption. So we can think any number that it should have these restrictions based on the conditions given. So maybe they are giving you information on the interval of x, or maybe something that's related to error, okay? Or maybe they give you the exact error. So if they give you the exact error, then I think it should be obvious that it should be going to be here. Your error. Okay. It should be less than 0.0021. So take the m equal to that number. And if you look on the 7, we can take this in terms of x minus 8, which get you -1 to 1. So we can take this as less equal 1. And then from here, we get the error based on our m, which is 0.0021 divided by 6. And this gives you the 0.0004. So if 7 less equal x less equal 9, the error will be equal to I think we can have a short break. Okay. Now another example that really elaborate more about the alternating series. Okay. If we have the approximation sin x, approximating the x minus x cubed and the question is asking what is the maximum error possible. When the interval is brought from -0.3 to +0.3.
use the approximation to find sine 12 degree correct to 6 decimal. And then the second question, or the third question, for what values this approximation accurate to within 0.00005. So we are stated that we have approximation using this equation, and then we need to know what is the maximum error possible from this approximation. From this point, which means this is the interval that we are going to observe. And then use the approximation to find the sine 12 degree to correct to 6 decimal. And then for what values of x, this approximation will be within the accuracy of 0.00005. So first, because if you remember the sign in Maclaurin series, when we are having the second derivative, and then the fourth derivative, and the sixth, and then all the even numbers, they will become 0, right? So our partial sum is actually P1, P3, P5, right? So if we want, we can define the sign first in terms of the series. Okay. This is the approximation. So the Maclaurin series itself for sine, for the Maclaurin series, so what we have is actually we are having 2 T5, right? So this is T5 x. And then for sure we have positive, negative, positive, negative, positive, negative all the time. So we know that for this series it's alternating. And then another requirement for us is if we let the coefficient here, or the number itself, if you look and if we compare with the successive terms, or the next term of the series, they will be smaller and smaller and smaller. 1/6, 1/120, and then smaller and smaller. Which means it satisfies our requirements for alternating series estimation. So since sine x is alternating, and the successive terms decrease also because the size of x is less than 1, because we are actually evaluating from 0.3 negative and to 0.3, which means that x should be less than 1. Okay, so since that satisfy the alternating series estimations, then we can use it for our calculation. So we can we can apply alternating series estimation. So what is alternating series estimation? So if we are going to approximate P5, our error will be the next term. Okay? That it should be easy enough to apply. Okay? So the error in approximate sin x by the first three terms is the next terms, which is the 7. And 7 factorial is 5040. Yeah, 967, yeah, 5,000. And then we have so error is smaller than, we can exchange x with 0.3. Or it's approximate 4.3. And then we are using these approximations. Sine 12. This will be equal to sine. We can divide and using the radian. So sine 12 is approximating pi over 15 minus pi yeah, more or less that's the sine 12. Or maybe just take the 6 decimals and take it to 12 like that. And then the second question, or the third question here, error is smaller than 0.00005. So we are going to use our equations, okay, and we need to find the x. So we will have x is, or x, we need to solve this, and this will be equal to 0.82. So when x is less than 0.82, then this is accurate within 0.00005. Okay, this is if we using the alternate series estimation. Okay. But actually we can also try to use the Taylor's inequality, because I think it's also more general. notice that if we use Taylor's inequality, since the second derivative of sine is negative cos x, so we will have at most it's just 1, okay, because it's sine and cosine. So the remainder also R6, this will be less equal than 1 over 7 factorial x with power of second. So if we look on the equation, is similar to what we have in the alternate series, right? So if we are trying to use the Taylor's inequality, I think we get at least similar numbers. And the other way we can solve this is by taking the calculators and using the graphs. If you would like to look on how the graphs will be, I think we can look on the partial sum of several n, okay? So sin x, and then p1, p3, 5, 7, and look here. This is when it's the best approximation. And we know from the example, it should be 0.8 something, right, from what they give information. And I think it's true that if you look on this points, I think nearby the 0, it will be the best approximation. If a little bit going right or a little bit going left, it should be having a gap in between all the parts of the sum. Okay, actually in your textbook they still have some application to physics, but I think we can just skip the physics one. In physics, there are two examples related to relativity, and then you will have the series for the velocity and the light speed of light. You have the series, and then the other application is for optics. Okay, I think we can just skip that out. Okay, later I will give you some exercise on this application, and I think the applications, like if you read the example, like for example this one, this is just some of the typical questions, like finding the error with some certain accuracy, and then maybe they are also giving you the numbers that we need to split to find the sum. Okay, I will let you know the exercise for the later part. So chapter 11 we conclude chapter 11. Let me check what else we have. I think we can just take review on chapter 11, giving you some practice, okay? Instead of going to chapter 12. Okay. Okay, maybe first let me give you questions. Find the sum of the series. Let me take this second questions. The first one. Find the Maclaurin series. Give you 3 questions. Okay, try this. These questions. Oh, and radius of convergence and radius of convergence. I think for finding a Maclaurin series, you can either take the functions, take the derivative, second derivative, and make it the Maclaurin series, or using the reference. For example, for the first one, you can use the sine x and exchange the x within the series. For the last one, you don't actually really need to use any knowledge of the series on chapter 11 precisely, but we can use some method. If you remember the telescopic sum, we can use that to approach the second. And the second question, I put these questions, I think last 2 years or maybe 2 years ago, as a exam question. So I think you can remember the second one. I think it's okay. It's fine. I think for sine, no problem, right? You can just exchange the x before with the sum of the series of sine x for Maclaurin. The second one, tan with power of x. No problem with it? No problem. Okay. Okay, so another approach before tan with powers of x, which means we remember that this is similar to the base 10 with power of x. So we can rewrite this as E. Can write like that. And we can just use E and then exchange this variable inside the sum. Okay. So I believe no problem here, but let me just write the example, or maybe write the sine x as the Maclaurin. So the sign x with power of 4 will be equal x with power of 4, so which will be x 8n plus 4 divided by 2n plus 1 factorial. And if you see some idea for you to see the sum, if you see sum like this, having power n and then factorial, the radius should be infinity, right? If you don't trust me, you can just use ratio test, and you'll see that this will be cancelled, and you will left by this structure of 1 over n. 1 over n is 0, so any x can possibly be your radius. Right? So radius of curvature will be 0. Okay, for the second one, we can take this in terms of e to the x. And then take the e with power of ln 10x. And then exchange all with 10 ln 10 x and then with power of n. And then this is also similar. Okay. You see, some power of n factorial. The radius is always infinity. Okay. Now the last one. The first step, okay, to solve this sum of the series, first is to rewrite the form. Okay, so we need to modify the form. So if you have this, let me write as okay. I think so far no problem. Okay. And the idea behind the ln is the ln will have some property that can separate these fractions, become the subtractions, right? And I think from there you know how the idea it will become the telescoping. So from here we can rewrite further that the n squared minus 1 become n plus 1 and n minus 1. And then we can separate this n plus 1, n minus 1, minus ln, n squared. And then we can take this ln n plus 1, and then plus ln n minus 1. So we are just taking times to rewrite the form first and make it into some at least we have looking at some expansion. And then what's the next step? The next step is quite tricky. So this formula and this ln n, I will separate this negative 2 ln n becomes 2 ln n and ln n, and both of them I will include in these two fractions. So I will write this as ln n plus 1 minus ln n. Okay, that is the first one. And then minus ln n plus the ln n minus 1. Okay. So this will become n plus 1 over n, and then minus ln n, or maybe if we take this, or maybe let me write with the other term first. Let me write this first. So this will be n minus 1 divided by n. You write more clearly. N minus ln n divided by n plus 1. And then we can take the sum we are using the partial sum, let's say as k, so we can have a finite value. And then we can take sum n from n equal to, so ln 1 over 2 minus ln 2 over 3, and then plus ln 2 over 3 minus ln 3 over 4, plus, and you will see where it goes. It will be telescoping sum, and then we have our formula for ln, k minus 1 over k minus ln k over k plus 1. And since we will have infinite number, let me write the ln first. So we will have, if we have k is infinity, we will have limit as k getting 0 of our partial sum of k. So limit ln half minus ln k plus 1, and we will have ln half minus, take limit for k over k plus 1 is 1, right? So it will become ln 1, which is 0. So we will have ln 1 minus ln 2 minus ln 1, or we will have negative ln 2 or ln half. Okay. Any questions? Yeah, this is, I think, quite complicated. When I was giving this question, I think in the classroom, only 2 students got correct. Okay, if there is no question, I would like to get some feedback from you. Let's play some quiz, okay, but I think take some time for write in the notes, and then we can play the quiz. And I need to see whether you are familiar with some of the methods. Because I know that chapter 11 is quite a lot from sequence, series, and there are several methods like swing differences tests and so on, comparison, blah blah blah, and then eventually we reach this second part of chapter 11, which is power series, Maclaurin, Taylor, application, representation functions. So the first part, sequence and series, is just looking on some pattern and then take some time to use some methods to make sure whether the functions or the series is converged or diverged, and from the series we can transform into a function or function to a sum of the series, and then we can use it to approximate some of the problem or a function. Right? So it's actually quite a lot of content. So I need to check how you familiar with this. So let's go through. Okay. At least this is from power series to Maclaurin. Okay. I will start. Okay, I will start. Okay, I will have at least 4 questions. And I need to check whether the time is okay. And the first one is the quick question. The first one is quick question. You can just use your logic. No need to have some series. Just use your logic. Just use your logic. It's just a very right? Okay, say it right 3 times and then input 0. Okay. Okay, who is both? Both? Okay. 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 Okay, get ready. Okay, 1 minute, around 50, 1 minute 60, I think should be enough, right? So already answered. Two person already answered. Very fast. Oh, 5. Oh, guessing. Another way to look at these questions, because you already given these options, then you can consider this from the options. Well, 12.
这样现在还没人做哪里？
有啊，4个了，就你最慢，
这样你选的是？
早就选啊，
你的话，
但不会啊，第一题还会约你就真的不会了。
猜。
哦。
OK。
Okay.
哎，我猜对了，还没猜赢。哇，那个 boat 真的很屌。
Okay, both.
第二个。
你这太会猜了。
那我太会猜，我第一个会。哎，猜对一题1/4没有。
Okay, 3, number 3.
抽中 AirPod 的嘛。
对啊，抽中 AirPod 比较紧哦。甩屁的嘛。
可以分
First。
哎，时间肯定够了，没有办法分讲了，上课然后一定。
Okay.
还是没有。
Is the time sufficient? No, really?
不是时间太少了。
你在抱怨，他妈用找的，然后干了抱怨时间太少。
来找那公生啊。
大家不会放弃，大家不会放弃。
看你现在可能要我的写。
You can actually think in secant as 1/10.
就算你知道这个，你也没办法解决什么问题，懂我意思吗？我不认为你知道它为一个什么，所以有办法解决这个一定是可以的。
太难做了。
Okay.
做了吧？
我自动跳出了。
Okay.
它自动帮我跳出了。
第一名啊，第一名。啊，有神猜，然后结果直接问他题感。
还有这个，不会了。
先选再想，算了。靠错了。啊！错了，选错了嘛，干选错了就选错了，他怎么说？就选错了，刚刚意思好。然后等下就说我错了，那就是真的是不好意啊。
Careful for this.
一定错了，我就说我错了吧。
为什么？
就错了啊，知道我错了。
Oh.
哎呀，两大都能猜。
Who's number 5?
谁啊？
Number 5? Okay, good. Okay, I think for the secant, if you check using 1/cosine, although cosine having plus minus plus minus, series, you will get the minus, right? So all the plus minus become plus plus plus. Right? Try divide 1 with the series of equal sign. You will get plus plus plus. Okay. Okay, I think that will be the end. And please check the Moodle around Wednesday or Thursday. I will give you, I think, a long period of time for clicking the link. At least you can choose which day you are going to click the link. So that will be the end for our class today.